were discussing about the derivations of the equation of motion for viscous flows last time, and let us just briefly see that what are the important conclusions that we had out of our previous derivations. So first we started with the general equation of motion, and we started with the integral form. From the integral form we derived the corresponding differential form with certain assumptions, and that differential form for linear momentum conservation along the direction I was written in this way. In the Cartesian index notation. So this is the first thing that we did, what is going to be the vector form. Now with the vector form you can clearly see that you may write this as the divergence of rho v into the velocity component that you are talking about. So you may use interchangeable forms. Our next objective was to figure out that how we may express tau ij in terms of the gradients of velocity and the fluid property, maybe one fluid property or two fluid properties or whatever. We figured out that in a most general case you might have required 81 independent constants to express the tau ij, the deviatory component of the tau ij with the rate of deformation. But at the end we found that if you have a homogeneous and isotropic fluid, it boils down to two scalars, and we could identify what are the important scalars for expressing the deviatory component of tau ij. So the first important thing is that what are the assumptions under which this equation is valid? Yes, what are the assumptions? Well, continuum hypothesis is valid, of course, that is otherwise you cannot write continuum conservation equations, but most important is that you have stationary reference frame with respect to which you are writing the equations. So if it is not a stationary reference frame and a very general case of a moving reference frame with rotation and acceleration, then you would have correction terms, and those correction terms may easily be derived by starting from the Reynolds transport theorem with the non-accelerating reference frame as the basis. So if you convert that to a differential form, you will get some extra terms, and those extra terms are because of the transformation of the reference frame. Now when we wanted to express the tau ij, the two components of the tau ij were like, one was the hydrostatic component and the other one was the deviatory component. The whole idea was that you have a component of the stress tensor which is a function of the deformation, and a component of the stress tensor which is not a function of the deformation, and whatever is not a function of deformation should also be prevalent in a case when the fluid is at rest, because when the fluid is at rest then its state of stress is something which is denoted by a simple normal stress condition, which is because of the pressure distribution, and that prevails or that manifests in this hydrostatic component. It does not mean that when the fluid is at motion it is not there, it is definitely there, but something additional is there which is attributed to the deformation of the fluid, and that we figured out that how we relate that with the rate of deformation. So we related this deviatory stress component with the rate of deformation by this one, where lambda and mu are two material property dependent constants. We figured out that out of our basic understanding of the viscosity and the effect of viscosity, that this mu is same as the viscosity coefficient that we learnt sometimes back in the elementary discussions in our course, and lambda is a constant which is sort of known as the second coefficient of viscosity, is related to the volumetric deformation of the fluid element, because this term is nothing but the divergence of the velocity vector. See here there is a index k which is a dummy index and it is repeated 3 times. So it is like first partial derivative of u1 with respect to x1, then plus u2 with respect to x2 and u3 with respect to x3. So that is the divergence of the velocity vector. So since divergence of the velocity vector gives the indication of the rate of volumetric deformation, so this part is related to the rate of volumetric strain and this part is related to the angular deformation. And angular deformation, we have seen that it is the shear deformation that matters for the stress, because the rotational component is a sort of effect that does not give rise to any viscous stress. So only the symmetric part of the deformation is what is going to give rise to the viscous stresses. What are the assumptions under which this is valid? See, Newtonian fluid is one important thing. So you have Newtonian fluid. The most important property that we have used is isotropic fluid. Homogeneous fluid will imply that this lambda and mu are not dependent on xi, or that is position. So if lambda and mu are dependent on position, still you may make a bit of more general form of this one, which is a form of a non-homogeneous fluid element or material. But if we assume that lambda and mu are position independent, then you say that it is also homogeneous. So let us for the time being assume that it is also homogeneous, that is lambda and mu are position independent. And so with these assumptions coupled with the assumption for stationary reference frame, it will now be possible to substitute the tau ij in terms of this one. So we have to keep in mind that the tau ij also had a hydrostatic component, and this hydrostatic component is something which we realize that is because of the pressure distribution, and it is a normal component. So we use the delta ij notation, when I equal to j only this is 1, otherwise it is 0. So that means when you are talking about a normal component of stress, then only this term comes into the picture. For all other cases it is 0. So remember that delta ij is equal to 1 if j equal to I and equal to 0 if j is not equal to I. Now we will try to see, or we will try to find out that what is this relation that is trying to give us. See, when we were talking about the equation of motion, this equation of motion had several unknowns. So one of the unknowns, or rather some of the unknowns are the velocity components, so u1, u2, u3, and the other unknown was the component, any component of the stress tensor. So 6 independent components of the stress tensor tau ij. Now we have expressed the stress tensor in terms of the velocity gradient. So no new unknowns arise because of this, but because of pressure there is a new unknown that has come into the picture. So if you substitute this form in the equation of motion, you will get how many unknowns? You will get the velocity components, independent velocity components, say u1, u2, u3 and pressure as the unknowns. We will try to see that how these equations and unknowns may be closed, because one important understanding is when you utilize this equation, you have to, your understanding is you have to solve for velocity and pressure, these are the unknowns, and at the most you get 3 independent linear momentum conservation equations. For angular momentum conservation you do not get any extra equation, because tau ij equal to tau ji that has already been incorporated in some of the derivations, you do not get anything new out of that. And we will see that still with 4 unknowns and sort of 3 independent equations apparently how we can close the system. But before that, let us try to look into some of the implications of these terms. So, we will first concentrate on the term P, the pressure. Some time back we were discussing about a concept called as the distinction between thermodynamic pressure and mechanical pressure, and we will revisit that again here. So, when we are talking about the pressure here, this is what, how do you feel the pressure or how do you relate the pressure with other parameters at a point. So, pressure at a point may be related with any other parameters at the same point through the equation of state. So, the equation of state may not be as straightforward as that of an ideal gas for any general substance, but any general substance will have some form of equation of state. For ideal gas it is like PV equal to nRT, that type of equation of state is there. So, thermodynamically what it means is that if you know at a point what is say density and temperature, you find out what is pressure by having a functional relationship with those. So, if you have two independent intensive thermodynamic properties, by that you are able to describe pressure as a thermodynamic property. So, it is a thermodynamic property because it is a function of two other independent thermodynamic properties. For the ideal gas it is like you are expressing it directly in a very simple relationship with pressure and temperature. For other substances density and temperature, for other substances it may be much more complicated and not as straightforward. So, this pressure that we are having here, we call it a thermodynamic pressure. We will see that how we distinguish it from a mechanical pressure, but to do that we will first write the normal components of the stress. So, we will write tau 11. So, what is tau 11? Tau 11 is minus P. Why we are only writing the normal component is because if we write the shear component, this P will not come into the picture. So, if minus P, then plus lambda. So, even the term with lambda, that also does not come into the picture for a shear component, and that is quite obvious because a volumetric deformation should not be confused with a shear. And then plus 2 mu right. Similarly, you can write tau 22, what is that, minus P plus lambda, the same thing. So, here I equal to 1, right. And tau 33 . So, if you now add these together, all these 3 expressions, what you get is something which is tau 11 plus tau 22 plus tau 33. Let us say we are interested to find out the arithmetic average or arithmetic mean of that. So, we divide it by 3. So, if we add and divide by 3, right hand side the first term becomes minus P. Then if you see, if you add the last 3 terms together, this and this, you will get this term, right. So, you can take here 3 lambda and here 2 mu as common with the del UK del XK term, and that when divided by 3 will become lambda plus 2/3 mu okay. This is very simple and straightforward. Now, the term which is there in the left hand side, this we call as minus of mechanical pressure. So what is mechanical pressure? Mechanical pressure is a sort of arithmetic average of the normal components of stress. The sign is adjusted because the positive normal component of stress is sort of taken as tensile and pressure by definition is compressive, that is why this with a minus sign it is adjusted. So this is the definition of mechanical pressure. We will now try to understand what physical meaning does it convey, but first the definition. So you can clearly see that we have a relationship that relates the mechanical pressure with the thermodynamic pressure, and the first and foremost observation is that in general they are not equal, because you have a correction term here. The question will be that when they are equal, when they are not equal, and what is the consequence of that equality or inequality. But to simplify things out, Stokes came up with a hypothesis which is known as Stokes hypothesis. Stokes hypothesis was that mechanical pressure equal to thermodynamic pressure. We will see that under what conditions this hypothesis works and under what conditions this hypothesis may not work. So Stokes hypothesis says mechanical pressure equal to thermodynamic pressure, that for a general substance will work only if you have lambda plus 2/3 mu equal to 0, that means lambda is equal to minus 2/3 mu. Since this is an hypothesis, obviously there was no proof of that, but there was some expectation based on which this hypothesis was postulated, and we will try to understand that expectation. See, mechanical pressure, what does it represent? It sort of represents the effect of the translational mode of energy of molecules, whereas a thermodynamic pressure, it sort of represents the translational, rotational, vibrational, all modes of energy of a system of molecules. So when you see the distinction will be because of the rotational and vibrational modes of energy. So one is representing only the translational modes of energy and one is representing the translational, rotational and vibrational modes of energy. But there are certain cases when you will not have a rotational and vibrational mode of energy, you have purely translational mode of energy. Think of a dilute monoatomic gas. So there you have a translational mode of energy is the mode of energy even when you look into it thermodynamically. So in that case you do not have any distinction between mechanical pressure and thermodynamic pressure, and then Stokes hypothesis is not an hypothesis, it is a exact reality, there is no deviation. But all substances, even if we think of gases or compressible substances, all substances are not dilute monoatomic gases, and therefore for all substances you will not have mechanical pressure equal to thermodynamic pressure. But we have to understand that what is the expectation. The expectation is, let us say that you have a bubble, inside the bubble you have some gas, and let us say that the bubble is changing its state. So when it is changing its state, what is happening? Say there is some change in temperature. So because of the change in temperature, maybe it is changing its volume, and maybe there is also a change in pressure. Now how this pressure, volume and temperature will be related, it depends on the manner in which it is changing its state or the thermodynamic process. So we are not going into the specific thermodynamic process, but we are just keeping it a bit abstract that by some thermodynamic process it is changing its state from say state 1 to state 2 to state 3, like that. So when it is changing its state, you have initially a pressure P, say P1. Now in the new state you have a pressure P2. So when you change the state from pressure state from 1 to 2 and there is a change in pressure from P1 to P2, now if you want to have the entire effect manifested in the form of a mechanical pressure, then you should allow a time which will make it locally equilibrate. That means the sudden change in pressure because of a change in thermodynamic state will give rise to a change in vibrational mode of energy, change in rotational mode of energy, everything, and eventually all these changes in equilibrium will be manifested in form of a change in translational mode of energy, solely manifested by mechanical pressure. So you should allow a time over which there is a conversion of all those modes of energy into the mode of translational mode of energy that is captured by the mechanical pressure, and that requires a time. So this is called as a relaxation time. So the relaxation time is very important. What is a relaxation time? So you are having a system, you are imposing a change to the system, and the system must have sufficient time to absorb that change and have changes in properties by local equilibrium, by having a new state of local equilibrium because of that change. So it should have a time over which it changes that state of equilibrium. It cannot be instantaneous. Because it cannot be instantaneous, there is a time scale which is called as relaxation time scale. Now if the time change that is taking place is so fast that the time scale of the change is faster than the relaxation time, then what will happen? Then the material will not be able to come to that equilibrium before a new change of state has taken place. So it is like the material is trying its best to come to a new equilibrium state at each and every instant, but till it is successful, again a new change has been imposed on it. So that is a very rapid process. Let us say that you have such a process in which a bubble is rapidly expanding and contracting. So if the bubble is rapidly expanding and contracting and it is doing with a very high frequency, then that high frequency means it has a very short time scale over which the change is being imposed, and this change what is being imposed is externally imposed, maybe because of a change in thermal environment, maybe the temperature is fluctuating very fast or whatever, and inside that the poor material inside the bubble is trying its best to adjust to that, but it is not possible to adjust to that if the change time scale is very rapid, and then it cannot equilibrate locally to come to a state when its mechanical pressure becomes equal to thermodynamic pressure. So mechanical pressure may not be equal to the thermodynamic pressure if the time scale of change is faster than the relaxation time scale. If the time scale of change is slower than the relaxation time scale, then yes, then whatever is the change in thermodynamic state, the system adjusts to that, eventually that mode is entirely transformed into a translational mode of energy reflected in form of a mechanical pressure. So the entire vibrational and rotational modes of energy should also be dumped in the form of a sole translational mode of energy, and that will be manifested in form of mechanical pressure. So it is a sort of like interconversion of one mode to another mode, and you have to give it that enough time for which during which it will do that interconversion. So the summary of this understanding is that if you have a very rapid change or a very rapid time scale or very fast time scale over which a change is imposed, a thermodynamic change is imposed on the system, then the system may not be able to attain equilibrium locally based on its relaxation time, which may be slower than that rate of change that is imposed, and then it will not be able to achieve a state when mechanical pressure is equal to thermodynamic pressure, and then Stokes hypothesis will be violated. But for most of the practical applications that we are concerned about, the Stokes hypothesis works, because usually the relaxation time scales for fluids, these are very fast. So and usually the changes which are imposed on a system are not faster than that. So whatever change is imposed on a system, at least locally at a point it tends to attain equilibrium, and that is called as local equilibrium. It is not a global equilibrium, that means it is not that throughout the system at each and every point properties are same, it is not like that, but at each and every point at least it sort of attains an equilibrium where its properties are related by equation of state, and eventually the interconversion from one mode to the other is possible, that time is available, and that is why Stokes hypothesis works for most of the problems. Only for a few rare cases where the change is so rapid in terms of the time scale, there it may not work, otherwise it is working. And therefore, when it works for the general case, see, you do not have the divergence of the velocity vector to be 0 in a general case, only for incompressible flow it is 0. So, for a general case, since the divergence of the velocity is not 0 in a general case, therefore, the other term must be 0. So, this lambda is equal to minus 2/3 mu is something which is obeyed for all fluids. There are certain fluids for which we do not care whether this is obeyed or not. What are those special fluids? One we discussed is monoatomic gas. So, if you have a monoatomic gas, you see that it has to be obeyed, not that we do not care whether it is obeyed or not, we do not care whether it is a hypothesis or not, then it is an exact reality. So, it is not a hypothesis anymore. So, for a monoatomic gas this exactly will be valid, and therefore, no question of approximating mechanical pressure with thermodynamic pressure, they are like exactly equal for a dilute monoatomic gas. But for other gases this is not an exact relationship, but this works because of the time scales that we talked about. For incompressible flows we do not care about this, that is the only substance for which we do not care about this, because its multiplier is 0. So, for an incompressible flow, since the divergence of the velocity vector is 0, the consequence is that mechanical pressure will be exactly equal to thermodynamic pressure. And the reason is that for incompressible flow you do not have to satisfy a new equilibrium state through such a equation of state, because equation of state is not very explicit for an incompressible flow. You do not have pressure density temperature relationships of the kinds, explicit kinds that you have for compressible flows. So, for incompressible flows you have mechanical pressure exactly equal to thermodynamic pressure. So, even if you say that I do not care whether Stokes hypothesis is valid or not, still it is okay for incompressible flow, so far as the analysis goes. Now, the other important observation is, if you look into the lambda, see the viscosity of a fluid is positive, that we have seen earlier. So, it clearly shows that lambda, which is the second coefficient of viscosity, will be negative. What is the physical consequence of that? So, look into say maybe one of the expressions, say tau 11. So, in the expression for tau 11, if lambda is negative, then you just look into or concentrate on the term that contains lambda. It is lambda into the divergence of the velocity vector. So, let us say that the divergence of the velocity vector is positive. That means what? That means volumetrically the material is expanding, because it is the rate of volumetric deformation. And if lambda is negative, that means the corresponding stress actually is reduced. So, more is the value of the divergence of the velocity vector, the corresponding proportionate change is actually less, because it is being multiplied with a negative term. What it means? It means that if a material or if a fluid element is already expanding, then the proportional enhancement in stress to expand it further is less, if it is implicitly already expanding. So, if you have a divergence of the velocity vector positive, that means it has a sort of tendency to expand, and therefore, the proportional enhancement in the stress that is necessary to expand it further is actually not an enhancement but a reduction. So, but if it is not already expanding, so if divergence of the velocity vector is negative, that means the stress that is associated with a further expansion is more if the divergence of the velocity vector magnitude wise is more. So, that is the important consequence of the negative sign of lambda. Not only that, it may be shown, we will not come into that here because it requires a bit of thermodynamics, and that is beyond the scope of this course, that not only you have mu greater than 0, you should also have lambda plus 2/3 mu greater than 0. So, when the equal to 0 is the special case, which is the Stokes hypothesis. If the Stokes hypothesis does not work, still it will be greater than 0, and the reason is that otherwise it would violate the second law of thermodynamics. So, because there is not enough scope to discuss about that, we will not go into that how this comes. It is very easy, once you go through the thermodynamics course you will be able to appreciate that it is very straightforward to figure out that why. but important thing is to understand at least at this stage that second law of thermodynamics gives you a restriction on certain natural processes or on certain on the ranges of certain properties. So, you cannot have all properties in all possible ranges, because the second law of thermodynamics restricts the cases that at the end of a process the total entropy of the system and surrounding should increase together. Entropy of the system and entropy of the surroundings together should increase at the end of a process, and if this is not satisfied then that is violated, and therefore it is possible to find out also the possible ranges of parameters. See, that is where there will be a difference between doing abstract mathematics and the physical reality. When we are talking about an abstract mathematics and if you are devoid of the second law of thermodynamics, you do not care, you may see like up to this no derivation has restricted really that this should be greater than equal to 0. You could use any value, say you may say that well I will use a positive mu. Till now we have discussed that you should have a negative lambda, but with many combinations of positive mu and negative lambda this may not be satisfied, but we have to satisfy this, otherwise it will violate the spontaneous change in a natural process that should be according to the second law of thermodynamics.